Hello, this is Information Service Engineering, lecture number 4, Linked Data Engineering. This will be the last part of this lecture, and here we are going to learn about linked data knowledge graphs. And let us start. So this is a slide that most of you should be familiar by now because we have seen it again in the course of these lectures. And the whole time here we are talking about linked open data. So linked open data, again, they denote publicly available RDF data, which they conform to the linked data principles, meaning that the data here, they should be identified via URIs and should be accessible via HTTP. And also this data, they should be linked to each other again via URIs. So currently we have almost 10,000 datasets in the web of data, and some of them you can see them here in the linked open data cloud. So those datasets, they contain more than 149 billion facts and more than 800 million links to each other. And let us zoom in a bit in this linked open data cloud we have here. So if we zoom in, we find DBpedia. DBpedia is a central hub in the web of data. It's an open knowledge graph. It's a general purpose or cross-domain knowledge graph, meaning that it contains data from different domains and is not focused in a single domain. And the data that DBpedia contains, they are extracted from Wikipedia. Also, DBpedia is a very widely used knowledge graph from several different research communities. So there are many different language versions in DBpedia, which of course correspond to the language versions of Wikipedia. And let us just see here some statistics or some numbers regarding the data that the English version of the DBpedia knowledge graph contains, as by June 2017. So in the English version of DBpedia, we have more than 4.5 million things, of which 4.2 million are classified in a consistent ontology. And if you visit this link here, you can see this ontology behind DBpedia, the DBpedia ontology. It also includes almost 1.5 million persons, 735,000 places, 411,000 creative works, including 1,023 music albums, 87,000 films, and 19,000 video games. It also contains 241 organizations, including 58,000 companies and 49,000 educational institutes. Also, it contains 251 species and 6,000 diseases, so lots of data which we are able to use, and we are very happy for that. So as I said, the data in DBpedia are extracted from the Wikipedia pages. And it's not only the data that they took, but they also try to keep a correspondence between the names of the DBpedia pages and the Wikipedia entities extracted by the pages. So here, if you see on top, we have the Wikipedia link to the page of the planet Pluto, which is our running example for this lecture. And what the people in DBpedia did, they took this last component of this URL, which is actually the name of the page, and according to that, they built the URI of the entity Pluto in DBpedia, as you see here, also the link to the HTML version of Pluto in DBpedia, and the link to the RDF XML version. So, there are two category systems in DBpedia. There are two ways to categorize entities in DBpedia. The first one comes from the Wikipedia categories. That means that a resource or an entity in DBpedia can be categorized based on the categories where the corresponding Wikipedia page belongs to. And this is how we do it. We use the property DCT subject in order to link a resource from DBpedia to the corresponding category of where also the Wikipedia page belongs. So here we see that Pluto is DCT subject of objects formerly considered planets. And this is again a hierarchy which we can traverse by using the Skos-Brodder property. So this one is Skos-Brodder planets, and Skos-Brodder astronomical objects, and finally Skos-Brodder physical objects. So this is the first category system. And the second category system is based on the DBpedia ontology itself, so the classes in the DBpedia ontology. So here an entity or a resource in the DBpedia, here we have Pluto, is linked via the property RDF type to the class in which it belongs, as we've seen in the previous parts of this lecture. So here we see that Pluto is RDF type planet, and we saw in the previous parts of the lecture how to traverse this hierarchy. And this we do it with the help of the RDFS subclass of property. So now we know that DBO planet is a subclass of celestial body, which is a subclass of place, and finally it's a subclass of all thing. As we've seen before, everything in the end is an all thing. Okay, so we said that the information which is there in DBpedia comes from the Wikipedia articles, but we didn't say from which part of the articles this information comes. So from the whole information that is there in the article, meaning the abstract and all the text is there, the answer is no. So the information that we have in DBpedia comes from the info boxes of the Wikipedia pages. So if you don't know, the info box is this box that you usually see on the right part of the page when you visit a Wikipedia page. Most of the pages in Wikipedia have an info box, not all of them, but most of them. And the data that we currently have in DBpedia, they come from the Wikipedia info boxes. So the first extraction framework in DBpedia, so that we can extract information from these info boxes, resulted the raw properties dataset. So this framework, it's a direct extraction of all the information that is there in the info box and added or translated into triples in DBpedia. So here they would extract a triple saying that Pluto has a discoverer or discovered by Claude Tombaugh. This is the information that we get from this info box. So the thing here with this first extraction framework is that I said they extracted everything. They didn't have any pre-processing steps or normalization steps, and this resulted to some thousands of properties extracted from the info boxes. So that's why the namespace that they gave to these properties extracted for the first extraction framework is dbpedia.org/property/ the name of a property, here discoverer, for example. But they have a second extraction framework which resulted the mapping-based properties dataset. So again, the information here is extracted from the info box of the Wikipedia page, but it's the information or the properties extracted are those that they conform to the DBpedia ontology this time, so not every property. And of course here there are normalization steps after or techniques applied after the extraction framework, so that they are able to generalize the domain in the range of a property, so that it can be used to model also a more general entity. So for example, here the property discoverer, if you see, has as a domain the whole thing and as range DBO person. So it holds between a thing and a person, which is rather general. So this property discoverer won't link only astronauts to planets, but something to a person. That's why this dataset is much more compact. So here we have some hundreds of properties in comparison to the previous one, and the namespace here is different. So here the properties in the mapping-based properties dataset, they follow the URL dbpedia.org/ontology/ the name of the property discoverer in this case. Okay, and we've seen some details about DBpedia, and now it's time to move to Wikidata. So Wikidata is again an open knowledge graph, a general purpose knowledge graph again, meaning that contains information from different domains. It's not focused to one domain. And here is a collaboratively edited knowledge graph operated by the Wikimedia Foundation. The Wikimedia Foundation is a foundation who also handles and maintains Wikipedia, among other projects they have. So this is how the page of a Wikidata entity would look like. We're going to emphasize more in the next slide. But what I want you to get from this slide is this options that we have of edit and add. If you noticed, I mentioned that this is a collaboratively edited knowledge graph, meaning that the information in there is not only extracted automatically from some other source, but in addition can be edited or edited and added by users. So you can become a user in Wikidata and add new information there, new triples, or even edit existing information in case there is a mistake, for example. And personally, I find this really cool. So let's go into one Wikidata page and see in details what we have here. So here is a Wikidata page of the entity Pluto, our entity for this lecture. So what do we see? First here we see an identifier next to name Pluto, this Q339. This identifier is the unique identifier for the entity Pluto in Wikidata and will be also part of the URI of Pluto. The URI of Pluto, you can see it here in the blue link on the right of the page. And actually, if you visit this link, you are going to be transferred directly to the page of Pluto in Wikidata. So what else do we see here? We see some statements. So the knowledge in Wikidata is organized into statements. So statements are those building blocks where they keep these pairs of values of property and value. This pair. So for each property in a Wikidata entity, there is a corresponding statement where it keeps all the information, let's say organizes all the information regarding the property and the values this property can have, because properties can be multi-valued, so they can have several object values. And speaking of properties, this instance of here is a property, as we already know what a property is. And Plutino here is the value of this property. So here we have the triple Pluto instance of Plutino, where Plutino is a value. Okay, so far all these things we've seen it before, but what we also have here and we haven't seen before is this 0 references. So in Wikidata, since it's collaboratively edited and people can add information there, they have this option of references in order to refer to some external data source in order to back up the information that you add there in Wikidata and support it further. Another thing that we have here in Wikidata is those qualifiers. They are called qualifiers. So this is extra information that refers to a specific triple. So this is not a general information related directly to the main entity here that we have here, for example, Pluto, but it's an additional information to support a specific triple regarding this entity. So this is information about Pluto instance of dwarf planet. And we see here that we have, for example, start time somewhere in 2006. Probably that is the first time that it was considered as a dwarf planet. And as I said, Wikidata is an open knowledge graph, so we can use it and we can query it. And normally as another RDF knowledge graph. They have their own SPARQL query service, and here is a screenshot of the SPARQL query service. We write our SPARQL query and then we get the results that they are there in Wikidata. So here in this query we want to find out which politicians have died not on natural causes. And this is the query and the result, but let's see, we can do it together. Okay, so if you click on that link, you will also be transferred here, and then you will have the query itself here so that you can check it or modify it accordingly if you want. So we start with the prefixes. We know what prefixes are, so we use the corresponding prefixes here for Wikidata, and then we have our select query. So select, distinct, we select for a politician and a cause, and also politician label and cause label. And then we start with a where clause, where we have to actually build our query. So, in the first line of the query, we want to search for some person who's a politician. So we want to have somebody who has as occupation politician. If you see here, everything is like an identifier, so you cannot really make sense of it if you look at it right now. But a nice feature here of this query service is that if you go with your mouse on top of it, you see exactly what is the property or the entity or the class behind this identifier. So here we see that this one is politician. So what do we want here? To find somebody who has as an occupation politician, and then we want to find the cause of death or the manner of death. So there are two properties. We don't know which one would be picked for each entity, so we go for the logical OR here. And so we have the cause, and this cause should be a subclass of homicide here, because we want those that they didn't die based on natural causes. So far so good, so this is our query. Something that probably looks weird to you because you haven't seen up to now is this line here, the service here. So this service is something that it's internally implemented to this specific query service of Wikidata, and to keep it simple, have in mind that it's something like the RDFS label. So you see already here that everything is an identifier. So we need the labels in order to really make sense of the result that we have. And by using this, exactly this line here, this command, this service, we are going to have also the labels behind the identifiers. Here I have specified the language, which is English. I want the labels to be in English, but you can change the language. So if you noticed, the variable that we have used here in the query is politician and cause. So in the query, we haven't used this variable politician label or cause label. We don't have to do it, but automatically by adding this service here, the query engine realizes, and for politician label and cause label, they will return the labels that correspond to those two variables that we have here. And let us run the query. So to run the query, we should click here on the run button or execute button. We wait for a bit for our results, and here we have our results. So you see that our result set consists of 4 columns here. In the first we have the politician, in the second the cause. You see that there are identifiers, although they are linked, so if you click on it, you will be transferred to the corresponding page of the politician here. And the politician label, as we saw, so this is probably the name of the politicians, and the cause label. You see everything here is a murder, because this is what we asked for. Great. So let us go back to our examples. Okay, and let's go for another example here, another query to execute in Wikidata. So a nice feature that they also have in Wikidata is that apart from returning this query result as we saw it before in the form of a list, you can do some other cool things like, for example, to directly produce a timeline out of the result of your query. And let's see how we will do that. So here I ask for a query, I want to find the timeline of all Roman emperors. And let's try to do it again together. So this is our query. In order to specify that you go for a timeline answer, you should put this second line here. So you should define the default view to be a timeline. And then we have our normal query where we ask for something which is an instance of a person or a human, and then the position held, which is similar to the occupation, should be a Roman emperor. And then I am also interested for the start time, because we go for a timeline, so the time here is important. And as you see, we have an optional of a picture. So if there is a picture also linked there, bring the picture as well. And in the end, we have again the service, so that we have the labels in also, not only the identifiers, but the labels as well. And what we want to do, we want to order the result of this query. We've seen how to order the results of a SPARQL query, the same stuff here as well. So order by, in descending order, based on the start time that we asked for. And let us execute this query and see what we are going to get here. Wow. And we have this really cool timeline of the Roman emperors. Cool, isn't it? So again, here these are links, so if you click on it, you will be transferred to the Wikipedia page of the specific emperor. Nice. So let us go back. So this will be the end of the linked data engineering lecture. And by now, you know what linked data is, what are the principles of linked data. You know about the vocabularies of RDF, RDFS, and NOEL, so you know how to build your own ontology. Also, you know how to query ontologies via Sparkle. And in this last part of the lecture, you saw two really important examples of open knowledge graphs. So please go ahead and start exploring here and querying the rest of this Link Open Data Cloud. So, if you are interested in basic machine learning, please don't miss the lecture of next week, because there we are going to talk about basic and machine learning techniques.